All right, folks, welcome to Significant Figures Notes. These notes are going to be fairly long and they're going to be pretty confusing at times. I think once you get it, you get it. But at first, you'll be a little bit deer in the headlights. So steel your minds, get ready, nerds, for a rough lecture today for some. Now, some quotes from previous students about this lecture. So these are students I've had before, and this is what they said about this lecture. I forgot my name at times. I hate zeros now. And prepare to be triggered. And those are all quotes from my previous students. These are things that they actually wrote down. So I'm guessing that by the end of the lecture, you may look something like this. This is you trying to explain SigFigs to your friends. So yeah, let's go ahead and start by doing a little multiplication times table. Do me a favor and do this times table here. So for multiples of 4, so 1 through 7. So hit pause real quick and do this times table. All right. So now that you pause in this times table, I'm going to go ahead and fill this out. Here we go. So 1 times 4 is 4. Sounds great. 2 times 4 is 8. Wonderful. 3 times 4 is 10. 4 times 4 is 20. 5 times 4 is 20. 6 times 4 is 20. 7 times 4 is 30. So yeah, pretty straightforward, right? I know that some of you are like, what is happening to me right now? By the end of this lecture, I'm hoping that you can explain this. So there you go. Some of you are like, I'm triggered, and it's been 2 minutes already. What's going on? Let's go ahead and get into those notes, folks. Let's talk about significant figures and errors associated with measurements. Okay, so why is this happening? Why are SigFigs a thing? Well, SigFigs tell us how good our data is or how good our tool is. If you remember from a lecture earlier this week, I measured the same square or rectangle, I think it was, with 2 different rulers. And my measurement changed not because the square changed, not because my eyes changed or my ability to measure changed, but simply because the tool was improving. And so SigFigs keep that into consideration. So if you guys remember these rulers from earlier this week, I just mentioned. So calculators don't care about SigFigs, by the way. So calculator isn't able to infer SigFigs, but you do. And you will be doing significant figures throughout the whole problem. Now you may be wondering to yourself, what do you mean my calculator doesn't care? What do you mean doing them through the whole problem? Just write these down and we will get to them. So again, during this lecture, you'll probably want to pause lots of times so you can kind of catch up with the writing because I will be speaking more quickly than you're writing. Okay. So that brings us to exact numbers. What is an exact number? Well, there's a few different scenarios where we have exact numbers. So any counted number, any given or constant, or any conversions, those involve exact numbers. So for example, in an equation where you have area equals 1/2 base times height, so that would be the area of a triangle, that is an exact idea. That's an equation that's exact, so there's no error there. Or if you're counting something like I have 1, 2, 3, 4, 5 dimes, there's no error. It's not like, yeah, 5 dimes plus or minus 1. It'd be like, no, it's exactly 5 dimes. There's no error there. Or a conversion like 2.54 centimeters equals 1 inch. There's no error there. That is a conversion. That's a perfect exact idea. There's no error. Now, estimated numbers. Remember, as we talked about measurement earlier this week, you read everything that you know, and then eventually you'll get to a point where you have to estimate. And once you estimate one time, you're done. But when you do estimate, you are introducing some error. So the observed value or quantity, aka the measured value. So anytime you ever measure anything, I'm not talking about counting or using an equation or doing a conversion, but every time you measure something, okay, you will have estimated at the very end of that measurement, and that means that there's some sort of error in that measurement, okay? So you never know for sure if your estimation is correct or not, and therefore you have a little bit of error every time you measure something. So again, exact numbers, talking about equations, counting, conversions, but measured values have some sort of error. They're not exact. Okay, so you can take a moment on this worksheet right here, this first section. Just go ahead and write the word either exact or estimated, referring to these 5 different values that were given here. Okay, so hit pause right now. Go ahead and try those. Okay, so if I'm looking at this, 132 people, that is an exact value, okay, because you just counted how many people there were. 800 miles long, well, that's some sort of measurement, and so that's going to be estimated because someone had to measure that. 10 dimes, again, is counting, so that's exact. 1 dozen eggs, again, that's exact. 10 millimeters equals 1 centimeter. That's a conversion, exact. Another conversion, exact. Conversion, exact. 24.1 centimeters, that's some sort of measurement, and therefore there's an estimated value at the end. 26.00 degrees Celsius, again, that's a measurement, so it's going to have an estimation. About 39 inches equals 1 meter. That's going to be estimated because that's not an exact conversion. It says the word about, meaning that there's a little bit of error estimation involved. Okay, so it's important to be able to distinguish between exact and estimated values. Okay, let's go ahead and move on. So now we're going to talk about the actual rules for significant figures. Okay, so first up, non-zero numbers. So that's your 1, 2, 3, blah, 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 all the way up to 9. Anything that's not a 0 always count as significant. Okay, so we have 3 measurements here. So 247 centimeters, 2, 4, and 7 are all non-zeros. So this has 3. I'll put SF standing for significant figures. 0.1491. Okay, all the 1, the 4, the 9, and the 1 are all non-zeros. And so those are 4 total significant figures in that measurement. 23.567, a 2, a 3, a 5, a 6, and a 7. Those are 5 significant figures because none of them are a 0. Okay, so that's the first rule for significant figures. Non-zero numbers always count significant. But then the zeros have special rules. Okay, now there are 3 kinds of zeros, so please pay careful attention. This may be a part of a video where you want to pause often to sort of make sure you're understanding, or you might want to rewind a couple of times to really grasp what we're doing here. So, leading zeros, okay? Leading zeros never count as significant. So you definitely want to write this down. Leading zeros never count as significant. So what do I mean by leading zeros? I mean any zero in a measurement that does not have a non-zero in front of it, okay? So this example right here, 0.0000543. Notice how there are no non-zeros in front of these 4 zeros, okay? So that means that these are leading zeros, and if these are leading zeros, they are not significant. So this measurement right here has 3 SigFigs, the 5, the 4, and the 3, but those leading zeros are not significant. Now, the next value, 0.093, so like, okay, so one of those zeros is after the decimal like the last problem, but one of them is before it. So does that change anything? The answer is no. Both these zeros are still leading zeros because there's no non-zero in front of them. And so this value only has 2 significant figures, the 9 and the 3. Over here, we have a million leading zeros, 0.00001 kilometers, but there's only 1 significant figure in this measurement because those are all leading zeros. Now, for the record, I'm going to use a different color here to distinguish. If there was, like, let's say there was an 8 right here. So this read 80.00001 kilometers. That would make all of these zeros no longer leading zeros. Okay, so that could change everything. So I just want you to know that leading zeros are only leading if there are no non-zeros in front of them. It doesn't matter where the decimal is. What matters is, are there non-zeros in front of them? And with these 3 measurements, there are not, and so that's why we got 3, 2, and 1 respectively. Now, another type of zeros are called captive zeros. So captive zeros always count as significant. Again, so you definitely want to write that down. Leading zeros are never significant. Captive zeros are always significant. Mr. Pilcher, what do you mean by a captive zero? Well, a captive zero is any zero that is in between, sort of think of like a sandwich, non-zero numbers. So right down here, we have 7,004 centimeters. Well, these two zeros, they are in between a non-zero 7 and a non-zero 4. And so they both count as significant. So we have 4 SigFigs in this value. These zeros, now they're after the decimal, but where the decimal is does not matter. Okay. These 3 zeros are in between a non-zero 1 and the non-zero 8 right here. And so they're all significant. And so we have 1, 2, 3, 4, 5, 6 significant figures in this value, or I should say measurements. And this last one over here, same kind of idea. These zeros are captive by non-zero 3 and a non-zero 6, so they count as significant. So we have 5 significant figures. Okay, so take a little breather, rewind this video if you need to go through leading zeros and captive zeros. And next we have probably the most confusing part of the whole lecture. So take a deep breath, because there's one type of zero we haven't talked about, and those are trailing zeros. So leading zeros are at the front of the number, captive zeros are in the middle, trailing zeros are at the end. And trailing zeros count only if there is a decimal. So it doesn't matter where the decimal is. The real question is there a decimal? If there is a decimal anywhere in the number, trailing zeros count. What do you mean by trailing zeros, Mr. P? Well, a trailing zero is any zero that does not have a non-zero after it. So 10.0 does not have a non-zero after it, so these zeros are trailing. But we see that there is a decimal right here, and if there's a decimal, that makes every trailing zero in this measurement significant. So we would have 3 significant figures in this first measurement. So we have 0.15430. So all of these values are after a decimal, but again, what matters is that there is a decimal. Okay, so there's a decimal somewhere, so that makes all trailing zeros significant. So this counts as 5 significant figures in this measurement. This guy over here, 100,000 grams. They put the decimal in there. So all those trailing zeros count as 6 significant figures. And so what does this really mean, this decimal? When a person puts a decimal in a number like that, what they're really saying is like, look, I know that this number looks suspicious, 100,000, but like, really? Did it actually land on 100,000 grams? But I actually measured those. I know those zeros, so I know these zeros, the first 4 of them, and I estimated that last zero. I know it sounds crazy, but they happen to land on the 0 mark. I don't know what you want from me. So by putting this decimal here, this person's saying, hey, I actually measured those zeros. That's what that is really saying, and that's why we count them as significant. Now, what about if we don't have a decimal? So instead of 10.0, we just have 10. So this is a trailing zero, but there's no decimal anywhere in this value. So we're left sitting here like, well, was it like more like 9 or 11 meters? Did you just sort of call it 10 because you rounded? Did you actually measure that zero? We don't really know. So we have to assume the worst and that they just rounded. So we're like, okay, there's 1 significant figure. And it's that 1 up in front. And that 0 doesn't count. That trailing 0 doesn't count because there's no decimal. So right here, 1,960 centimeters. Again, did they actually measure the 0 at the end here? Was it more like 59 or 61 and they just sort of rounded to 60? We don't know. So we have to assume that they didn't because they didn't put a decimal saying, hey, I actually measured these. So this only has 3 significant figures because that trailing 0 does not count as significant. This is the exact same number as above here, but we're missing that decimal. So now this person's like, yeah, it's like 100,000 grams. Like, did you measure those? But like, well, I know it's 100,000 something, but I'm not for sure about the rest of those zeros, so I just kind of made it a nice, clean, rounded number. So like, okay, well, there's only 1 significant figure. You only measured 1 thing in here. This person up here measured 6 values. That's why there's 6 SigFigs. But this person down here only measured 1 value. So that's why there's only 1 SigFig. Now, for the record, if there was a decimal here, all of a sudden that would change this to 6 decimals. I'm sorry, 6 SigFigs. But there's not, so we have to assume they didn't actually measure those. Now, you can go ahead and find this worksheet. So this is the back of one of the worksheets, I believe, or maybe it's the bottom half of one of them on your Unit 2 packet. So it says circle the significant figures in each of the following estimated measurements. So some of these are pretty easy. See 1, 3, and 7. Those are all non-zeros, so all 3 of these are going to be significant. But then when you start getting to zeros in values and measurements, that's when you have to sort of diagnose a little more thoroughly. So this first one that has a 0, 620, first thing I need to ask myself is, what kind of 0 is that? So it's a 0. There are no non-zeros after it. So it's trailing. It's at the end of the number. So it's a trailing 0. Then I ask myself, when do trailing zeros count as significant? When there's a decimal. I don't see a decimal, so that means this trailing 0 is not significant. So I'm going to go ahead and circle just the 6 and the 2. And you kind of go on as you go through this worksheet. So when you have no zeros, you pretty much can just circle the whole thing. But once you start getting zeros, you have to ask yourself what kind of 0 it is and is it significant or not. So I'm going to give you guys hit nice pause right here, spend some time working on this, and then we'll go over some of the answers in a little bit. Now that you've had some time to work on this worksheet, let's take a look at the answer key. The numbers in red are the ones that are considered significant parts of the measurement, and the ones that remain in the black ink are considered not significant in their measurement. So some ones I'd like to point out here to you. Okay, so check this out. We have a few different types of zeros in this problem right here. So the zeros left in black, so those are leading zeros. There are no non-zeros in front of them. It doesn't matter that there's a decimal. It doesn't matter that the first 0 is in front of it, that the next 2 zeros are after the decimal. If there are leading zeros, they're never significant, and there's no exception to that rule. This 0 at the end here, though, that is a different type of 0. That is a trailing 0. And since there is a decimal in this measurement, this person's saying, hey, I actually measured that 0 at the end, so it counts as significant in that measurement. So I would go ahead and take a look at all these. You need to make sure that you are doing well on these. So you need to compare your answers to this answer key here. If you're still struggling, you should hit pause and redo some of these problems until you feel like you really understand what's going on. Because on the next slide, we're going to start to calculate using significant figures. But if you can't count them yet, you won't really be able to do those multiplication and division problems on the next slide. So make sure you really get this section first. So maybe hit pause right now and double check your answers before moving on. So now that we're moving on, we got to talk about the rules for multiplying and dividing with SigFigs. So we are going to finally explain the whole times table for 4. So if you guys remember earlier in the lecture, this whole mess, 3 times 4 is 10, 4 times 4 is 20. How do you guys not know that? So that's finally going to get explained here on this slide. So, oh goodness. All right. So if I'm going through these values here, 3.0 times 4.0 is 12. 3.00 times 4.0 is 12. 3.000 times 4.00 is 12.0. 3.000 times 4.000 is 12.00. Mr. Pilcher, what the heck? What's going on here? Let's count our SigFigs, shall we? So 3.0 has 2 SigFigs. That is a trailing 0, but there's a decimal, so it counts. 4.0 has 2 SigFigs. And notice our answer has 2 SigFigs. 3.00 has 3 SigFigs. 4.0 has just 2 SigFigs. And notice our answer remains at 2 SigFigs. 3.000 has 4 SigFigs. 4.00 has 3. And so our answer can have 3 SigFigs. When they both have 4 SigFigs, our answer can have 4 SigFigs. So the name of the game is your weakest measurement in terms of the number of SigFigs will determine how many SigFigs your answer is allowed to have. So when we have 1 significant figure times 1 significant figure, that means our answer of 10, because there is only 1 significant figure. Okay? So the number of significant figures in the numbers that you are multiplying or dividing will determine the number of significant figures you're allowed to keep in your answer. So the number of SigFigs in the weakest measurement, in terms of the number of SigFigs, controls or limits how you round. So if we kind of show this to you in a different way, 3 significant figures, so whatever this measurement is, if it has 3 significant figures and you multiply it by 2 significant figures, your answer will have 2 significant figures in it. So I should write SigFigs after that. If you have 6 significant figures times 2 significant figures, you still only have 2 significant figures. 3 SigFigs times 3 SigFigs, you have 3 SigFigs. 6 significant figures times only 1 significant figure means you only get to keep 1 significant figure. So that's how these will work. You count the number of SigFigs that you're working with, and that will tell you how many you're allowed to keep in your final answer. And the rules for multiplication and division are the same. So watch. As I go from this slide to the next slide, the only thing that will change is going to be right here, the multiplication symbols. So the only thing that changes here are the multiplication symbols, these division symbols, and you still have the exact same answers, okay? So multiplication and division have the exact same rules for how many SigFigs you're allowed to keep in your final answer. So let's talk about significant figures off of a calculator. Again, this could be a good time to take a quick pause, get like a Snickers or something like that. We're almost towards the end of this marathon, so maybe pause the video for a quick break before I go on. Okay, so significant figures off a calculator. Please remember, calculators don't care or understand SigFigs, but you do. That's very important, especially when it comes to rounding. Okay, so when you're rounding, you don't chop the number off. You just simply round. You smooth it over. You make it prettier. So let's talk about this math problem. 135.82 times 17.00. Okay? So if you plug that into your calculator will tell you 2,308.94. Now we need to talk about how you would round that value. If you're allowed to only keep 5 SigFigs, so notice that we start with 6 SigFigs from the calculator. But let's say you're only allowed to keep 5 SigFigs based on what you know about your measurements. Okay, well then you'd keep the 2, the 3, the 0, the 8, the 0.9, and you need to round after that. So the 9 is your 5th significant figure. You need to round after that. Well, 4 rounds down, so this will just end up as 2,308.9. If we had to round after 4 significant figures, okay, so we'd have 2, 3, and so this 9 will round that 8 up, so we have 09. After 3 significant figures, so we start with the 2 and 3 again, and that 9 will round this 10's place up to just 10. Now notice I didn't chop the 9 off. I just rounded it out, okay? So some people, when they're getting to the 3 SigFigs here, here's what they're going to do. They're going to do something like this. So they're like, okay, 2309, but I can only keep 3 SigFigs. So what they're going to do is like, all right, I'll just chop this guy off right here. And so boom, 230. Or they might say something like this. They might be like, okay, well, that 9 tells my 1, so 200, oh goodness, 2309. Like, okay, so that 9 tells this 1 to round up. So I'm going to write that 0 as a 1, and so I'll call this 231 or something like that. If you're getting a little confused, that's fine because this is a mistake that you don't want to make. The point is you just don't want to chop this off. So notice how this is still the same size number. It's still a little over 2,000. We didn't chop it off. 2 significant figures. So we keep the 2 and the 3. That 1 rounds that 3 down, so just going to say 3. And so 2,300, again, still about the same size number. We're not chopping, we're rounding. Or we're allowed to keep 1 SigFig, we just call this 2,000. Okay? So again, rounding is more like a smoothing over with zeros. So you're sort of smoothing things over with zeros, okay? You're not chopping numbers off. You're not decreasing the size of the number or the measurement. You're just sort of smoothing it over. So please keep that in mind. So now that brings us to this worksheet right here, okay? Calculations involving significant figures. So I would like you to work on this. Now below this section, there's addition, subtraction. Don't worry about that at all right now. We'll get to that tomorrow. So just don't even look at that section. It's going to stress you out. don't worry about it. But I would focus on the multiplication and division section. If we do maybe a problem here together, let's see. Okay, so let's do 9.988 times 0.003. The first thing I want to do is I want to count how many SigFigs each one of these has. 9.988 has 4 significant figures. 0.003 only has 1 significant figure. So my answer is only allowed to keep 1 significant figure. So if I plug that into my calculator, so 9.988 times 0.000 or 003, that will come out to be something like this, 0.029964. So that's what my calculator tells me, because my calculator doesn't account for SigFigs. But I know that I'm only allowed to keep 1 SigFig. So my first SigFig is this 2, and I have to round after that. So this 2 with a 9 after it rounds up. So my real answer will simply just be 0.03. And again, that's because this only has 1 significant figure. So this is going to be a tough worksheet. You need to do a couple, check a couple with the answer key. Please don't go too fast. And please email me if you have questions. I can help you out. And don't worry, we'll do lots of practice at the beginning of tomorrow's lecture before we get to addition and subtraction. We'll do lots of practice in live lecture on Wednesday. So please just make sure that you are practicing a lot, okay? Good luck.